As we're talking about these statically indeterminate systems, there's another method we can use that might be a little more popular with some. I personally like this method a little bit more than the flexibility method. It's totally up to you. Either method will give you the same result. But in this flexibility method, in the compatibility method, we kind of flip the flexibility method on its head. So this compatibility method, what we're going to do is obviously free body diagram. Free body diagram is always first. Free body diagram and set up your equilibrium equations. So the reason I really like this one is because it feels really natural to start this way. We start all of our statics problems with lining out what our free body diagram and equilibrium equations are. So to me, it feels really natural to start the problem that way. Again, totally up to you. But for this method, we will write out our free body diagram, write out all of our equilibrium equations, and then from that point, we will set up some geometry relationships. So now we will draw the displacement diagrams for how this thing is moving. Right, so in our last one, we had that superposition first, and then we did displacement diagrams, then we did load equation, then we did equilibrium. Here, we're going to draw our displacement diagrams and create those displacement relationships. So that we can use our load displacement equation, which again is our delta is A over E. That's our load displacement for axially loaded things. And then we can solve for reaction. So really all it does is kind of change the order around and how you approach this. But either way is totally okay. They give you a little bit different setup and execution as you go through the problem. So what we're going to do is look at that example that we did with the flexibility method. We're going to look at that exact same example, but now using this compatibility method. So here we're looking at the same example that we did in the last video, determining the reactions at A and B when we have this little pipe that is fixed between A and B with a 500 Newton applied load on it. So again, our free body diagram for this is going to be the same. Right, we have our little rod here, we have the reactions at A and at B from the wall pushing against this, and that 500 Newton applied load. I guess I should say, I say these reactions are fixed, but in reality, there's only one axial load on this. There's only Y loading on this. So any moments or those X things, the X forces that we think of at a fixed location would really just be negating each other, right? Even if there were some X reaction at B, it would negate X reaction at A. So we're really not interested in it. So this loading is really entirely in the Y. So again, two unknowns and one equation. So our one equilibrium equation here, sum of forces in the Y direction equals 0, which is going to be FA plus FB minus that 500 newtons is 0. So this is the first equation we have to work with, and now we're going through and trying to find a second equation so that we can solve this, right? It's statically indeterminate to the first degree. We're going to need one more equation so we can solve. And that's what we're going to do by working with our geometry and our displacements. So looking at our geometry here, by geometry, we know that the displacement of B with respect to A is going to be 0, right? We know displacement has to be 0. So we can, from our axially loading geometry that we talked about a few videos ago, doing segments. Let's do this, I guess, in orange. We know that delta B with respect to A has to be 0 because it's touching that wall, right? The wall's not moving. The wall's not going anywhere. So that pipe can't go anywhere. There's no extra room for it to move. Displacement has to be 0. And we know from our axial loading that we can break this up into sections, right? We can break up our rod here into section of FA loading and a section of FB loading. Right, so here's FA, here's FB. So we know that delta B with respect to A is going to be our delta, this is point, let's call this point C, I guess, is going to be the same as C, point C, C, A, C, B, point C with respect to A, plus B with respect to C, right? So the displacement of each of these two segments here is going to be the same as the overall displacement. If we add those together, it'll be the same as the overall displacement. So this equals 0, right? This guy, he goes to 0, and we can find this D with C with respect to displacement of C with respect to A and displacement of B with respect to C with these little diagrams that we've drawn. So this is 2 meters, this is 3 meters, and we can set up those load displacements with our axial loading equations. So 0 equals D with respect to C is going to be coming from this guy right here, FA times 2 meters over area times modulus of elasticity minus, this is a minus because FB is in compression, right? FB is in compression, so that's a negative force times 3 over AE. So again, we weren't given area or modulus of elasticity, and again, we still don't need them because they cancel out. They're really not necessary for us to do this calculation. It could be any material of any area that this relationship holds true, or specifically for this geometry, I should say. So if I simplify this, what I end up with is FA equals 1.5 times FB. And now I have a second equation, right? So I have this relationship of FA and FB. I have my equilibrium equation relationship. So where is he? He's right here. So I can substitute that in. 1.5 FB plus FB minus 500 equals 0. And when I solve that, I get my FB is 200 newtons and FA is 300 newtons. Right? Exact same answers that I got using the flexibility method. So you can use either method, right? It's up to you. We got the same answer either way. A little bit different equation formation, right? They look similar, but here we have a relationship of FA and FB, whereas in the other one, our displacement relationship was between the load and FB. So they shook out to be slightly different equations, but we got to the same endpoint. So use whichever method you like more, you feel more comfortable with. I personally like the compatibility method, so I'll do another example of how we might use this, maybe a little bit more complicated example so you can see this in action. So in this example, we have a bolt inside of a tube that's initially sitting snug inside the tube. So it's not producing any force yet or anything. It's tightened as tight as it can without really producing any force. But then we're going to go ahead and turn it 1/2 turn. And we want to find out what the stress is in the bolt when we tighten it that 1/2 turn. So it gives us the modulus of elasticity for this bolt and the tubing, as well as the radii for both of those things. So it's a little bit tough maybe to draw this free body diagram if you're just looking at this, right? There's no applied force here. It's kind of an internal force acting on the cap here, the cap of this bolt that we have, right? Where if we were to take this kind of cut section, where we have the tube and then the bolt on the inside here, what we would see that we have is the force of the bolt pushing upwards and the force in the tube pushing downwards. So it's these kind of internal reactions that we have going on in our free body diagram. So our bolt is pushing up and our tube is pushing down. They're each taking a give and take of the force, right? Tightening that bolt. So this is kind of a representation of a free body diagram, kind of. Really what this does is allows us to set up an equilibrium equation, right? So here, our sum of our y forces is 0, which is just going to be our force in the bolt minus the force in the tube. So thankfully this just gives us a really simple relation of that the force in the bolt has to equal the force in the tube. That's simple enough, right? Now we'll just work through our compatibility equation and load displacement so that we can bring it together and have a secondary equation to substitute this force bolt equals force tube into to solve for each of those. Because once we get the force of the bolt, then we can get the stress. That'll be pretty easy once we have the force. So we're going to do our compatibility. Right now it tells us, I shouldn't have scrolled down, it tells us here that we're going to tighten it by 1/2 turn. And when we tighten it by 1/2 turn, it also says here that the bolt has 20 threads per inch. 20 threads per inch. So if we take this 20 threads per inch, and we're going to multiply by 1/2 turn. So it's moving through 1/2 of a thread. 1/2 thread, and then we have 20 threads per inch. That's going to give us 0.025 inches. Is that right? No, it's a division. Sorry. It's 1/2 divided by 20 threads per inch. So you're moving it half a thread divided by 20 threads per inch. And that's going to give you 0.025 inches. Right? So that's the displacement that this bolt is actually moving through. So if we kind of do a displacement diagram of this, here's our bolt and tubing combo. Well, it looks better than how I've drawn it here. So we're saying if this is going down, this full delta is 0.025 inches. That's the displacement that it's going to go through as we tighten it that 1/2 turn. This means that our delta tube and our delta for the bolt together must equal that displacement. Right? The tube is pushing it down by this much, the bolt is pushing it up by this much. Our displacement for the thread plus the displacement of the bolt has to equal that 0.025 inches. So these two displacements combined, they give us this. So that basically sets up our geometry of what's going on. That's our compatibility for this, our compatibility equation. Then we can go and substitute in our axial load equation. Right, so we got 0.025 is going to be Ft, force in our tube, and our tube is 3 inches long. Looking at our diagram, our tube is 3 inches long, and that is over area of the tube times modulus of elasticity of the tube. I guess we could substitute those in. No harm in putting those in right now. That would be, let's see, our area of the tube. We are given a radius, so pi r squared. Pi times 1/2. Now note that the tube goes around the outside of the bolt, so we need to subtract out this bolt portion, right? This is only this outer portion here. This is the area. So it's pi 1/2 minus that 1/4 squared, right? Subtracting out that bolt radius. Only the tubing is what we care about. And then the modulus of elasticity they gave us for the tube was 6480 KSI. 6480. Perfect. And then we'll add on the force in our bolt times the length, which again is going to be 3 inches. Same length for both. And then our area is pi r squared. Our radius is the 1/4 inch that they give us. So 1/4 squared. And then the modulus of elasticity for the bolt, it gave us as 10,600. 10,600 KSI. So now we've got this big, ugly hunk of an equation that we can simplify down to combine with our equilibrium equation, right? FB equals FT. Thank goodness that guy was simple, because we can use that to simplify this guy down, right? Make some substitutions, substitute in for FB or FT, and solve this. So we can go ahead and solve this guy, and when we do that, FT is the same as FB, which is 11.2 kips. Now remember not to stop there, right? We found the force of the bolt and the force of the tube, but it asked us for the stress in the bolt. So now we know how much force it's producing from being tightened down by 1/2 turn. So we can do our stress is the force of the bolt over area of the bolt. And that is going to be 11.2 over pi times 1/4 squared. So that gives us that the stress in the bolt is 57.2 KSI. Ta-da! This could be really helpful for checking if your math holds true, like if you are still in the linear elastic region, right? Make sure that you're not yielding, because if you are yielding, then everything that we've done is incorrect. We can't actually use these equations. So it can be helpful for checking that everything holds true, checking that the bolt itself can withstand the stress, right? Maybe if you tighten it that 1/2 turn, it goes to failure and your bolt breaks, right? So this can be helpful for calculating the stress and the displacements. That's what we use in these. With these statically indeterminate systems, we can find the reactions, we can find forces, we can find displacements, and relate those for whatever need we need to use them for. So for this last example, I want you to see if you can work this out on your own. It can be kind of difficult to work out the geometry for this one, but I have every confidence that you can do it. So we're given this system of 3 A992 steel bars that are pin connected to a rigid member. If a 15 kilonewton applied load is added, determine the force in each bar. So this is our layout, right? We have this 15 kilonewton applied load, 3 equally spaced bars, cross-sectional areas are given. Go ahead and try out this problem. If you're having a little bit of trouble with the displacement diagram for this one, before we get to the solution, your displacement diagram, what's happening here is that we have the load off to one side, and all of the bars are able to have displacement themselves. So each of the bars, right, if we have this initial position for A, C, and E, what happens first is the bars extend downward, and then that force is pulling bars A and C more than EF. So everything is being shifted down first because point E is being shifted down. There is a displacement in EF. And then it's also rotating. So first there's this displacement because of E. So this displacement here is because of E. But there is also this kind of triangular displacement from C and D due to this 15 kilonewton force. So here we have this delta, this here is delta C, and this here would be delta A, the displacement for member AB, DC, and EF, right? So it's important to bear in mind that this shift happens first. This DE shift maintains for every single one of these. So if you're doing a compatibility for these, DE, if you're doing a compatibility for these to determine, say this is 0.4, this is 0.8, you're doing a compatibility using the triangle here, just know that the way your triangle shakes out is going to be this distance, right? This distance right here is DC minus DE. That's the part of this triangle. And then you can just use the 0.4, right? So this portion of the triangle is DA minus DE. That DE needs to be subtracted out because it's going through that shift down before it goes through that angle shift. Right? So this would be the correct displacement compatibility equation to use for this problem. So having this displacement equation, go ahead and go on and see if you can solve for the forces in each of those three rods. So from here, I'll kind of briefly go through how we would go about solving this. Now, I did give you the displacement diagram here, but I skipped the very first step, which is the equilibrium equations, right? If we did our free body diagram here, we would have force in AB, force in CD, force in EF, and the 15 kilonewtons. So what we can see here is we have three unknowns and two equations we can use, right? We can use the moment equation and we can use our sum of y forces equation. So our sum of y forces, pretty simple. It's the A force plus the C force plus the E force, minus, that's a minus the 15 kilonewtons. And then we can also take a moment equation. You can take this moment wherever you like. I'll take it, I'd say maybe about point C. And we could take a moment about point C here and do FA times its distance away. This is a negative FA, was 0.4 plus the 15 kilonewtons times its distance away is 0.2 plus FE times its distance away is 0.4. So I have two relationships here, and I need a third equation to solve for my third unknown, which we can get from that displacement equation that we found, right? Using this triangular setup of how the displacement would actually go, right? Using this, I can substitute in my load equations. So if I were to simplify this down a little bit, I would simplify this down before I do that substitution. Displacement of C is 1/2 displacement of A plus displacement of E. So that's just a little bit cleaner equation to work with. And then I'm going to go ahead and substitute in my load displacement, my axial load displacement equation. So that will give me FC times the length. Now we'll notice that they're all the same length, I believe, right? We all start with this initial length of 5 meters, 0.5 meters, sorry. 0.5 meters. And they're all made of A92 steel, so they're all going to have the same modulus of elasticity. The only thing different is their areas. A and E have 50 millimeters squared, but C has 30 millimeters squared. So our A for this one is going to be that 30 millimeters squared times E is 1/2 FA times the length of A over 50 times E plus FE length over 50E. So I notice that my lengths all cancel and my modulus of elasticity all cancels for each of these. And if I go ahead and simplify this out a little bit, I get FC is 0.3 FA plus 0.3 FE. So now we have 3 equations and 3 unknowns. We can take our FC here, substitute back into this equilibrium equation up here, solve for FA or FE, and substitute into this moment equation here, and get our final answers. So I'm going to spare you the algebra solving systems of equations here. I have great faith that you all can do that. So we will just check our final answers, which should be you get FA is 9.52 kilonewtons. FC is 3.46 kilonewtons. And FE is 2.32 kilonewtons. That's just after solving those equations in our calculator. And that's it.